As we've studied each new type of function all semester long, we've added something like, it's still a function of this type if it's composed with something linear. So for example, here we have an absolute value with something linear happening inside and something linear happening outside. Something linear happening inside, something linear happening outside. This one just has something linear happening inside, and then outside nothing's happening. But these are all absolute value functions. So here I have an exponential expression, something linear happening inside, and then subtracting 7 is something linear outside. Something linear inside, something linear outside. And this one again just has something linear happening inside. These are all exponential functions. And then here we have a bunch of square roots with something linear inside and outside. Something linear inside and outside. Something linear inside and outside. These are all radical functions. And in fact, they're all specifically square root functions. So we have the basic function type, which we think of as kind of the important thing that's happening here, an absolute value or an exponential or a square root. And then all this linear stuff. And we saw, when we worked with them, that these families of functions have a lot in common. We find their ranges and domains the same way, and their graphs have the same basic shape. So what's so special about composing with something linear that the graph keeps the same basic shape? But if we compose with something exponential, say, that takes over the function's entire life. Well, it turns out that composing a function with something linear has the effect of a geometric transformation. What do I mean by that? We have 4 basic types of geometric transformations. And these terms might be something that you've encountered before. If not, they're really important terms to learn, definitely for this unit, and very much in pre-calculus and calculus as well. So a translation moves a figure left, right, up, down, sideways, moves a figure without changing its shape or orientation. So that means we don't turn it, we don't flip it. Scaling stretches a figure while preserving its basic shape. Reflecting flips a figure across a line without changing its size or shape. And rotating turns a figure around a point. So if we're going to translate, we need a distance and direction. If we're going to scale, we need a factor and also a center, though we'll often be very quiet about what the center is when we're working in a coordinate plane. If we're reflecting, we need a line. And if we're rotating, we need a point and an angle of turn. So in this figure, we see what happens when we transform the red shape. Here we've translated the red shape 2 units to the left. And notice every point on the red shape has moved uniformly 2 units to the left. Here, we've scaled the figure horizontally by a factor of 2. So, in fact, this was the center of our scaling. Every point got twice as far from the middle horizontally, while staying in the same place vertically, and the result is a figure that's twice as wide. Here we've reflected the red shape across the dashed line. So every point is the same distance away from the dashed line, but on the opposite side. And here we've rotated the shape 90 degrees around the point. If I draw from a point on the red shape to the point I'm rotating around, and then to the corresponding point on the blue shape, that's a 90-degree angle. So every point is 90 degrees away from where it was before, after the rotation. So those are our 4 kinds of transformations. We're going to limit the transformations that we talk about in the coordinate plane to horizontal and vertical translation and scaling, reflection across the x and y axis, and rotation of 180 degrees around the origin. Because those are the ones that are easy to play out in the coordinate plane. So that's what we're going to see for most of the rest of the lesson. What do we do to the expression of a function in order to get those geometric transformations to the graph? And therefore, how are those geometric transformations to the graph reflected in the expression for a function?